So now we're starting with Foundations Part B, the second half of this big Chapter 2. This part we're dealing with excavations and shoring systems, and then we'll move into asphalt and roadbeds, and then circle back to foundation science where we began when we were starting Chapter 2A. So what still stands true is what you see at the very bottom of this page. It says a foundation supports the building structurally, and it keeps moisture and organisms away. So first of all, starting with excavation and shoring. When you first excavate, you can end up with a trench that can collapse or an excavation wall that can collapse and bury people alive. It's very dangerous. So one of the ways we can deal with this is by sloping the sides of the excavation wall at a gentler slope so that it can't collapse. So the steepness of that slope depends on what type of soil you have. And we cover that in detail in our construction safety course. But here we need to deal with the actual structure of when you decide you can't do that and you have to build a shoring system. So yes, you can sometimes bench instead of slope if the soil is of good enough quality, but the same principle is still true. But here, what we're really looking at is when you can't do that, you build some kind of an in-place shoring system, or you use a trench box. But an in-place shoring system is what's needed if you're building a construction, if you're constructing a big building of some sort. So let's see. Shoring systems, the most common thing is really a sheet pile system. Sheet piling can be vertical planks of wood, or it can be steel I-beams, or it could be steel sheets of metal, and or it could be precast concrete piles that are either way driven tightly against each other into the earth. Sometimes you can take a wider sheet of metal and vibrate it if the soil is soft enough, and that happens a fair amount in Louisiana. In levee construction, sometimes they do that. And then soldier beams and lagging, the second bullet on this page, is a special kind of sheet piling, and I'll show you that. It's kind of an old-fashioned idea. And then there are other shoring systems, such as shotcrete, slurry walls, and soil mixing, so I'll talk briefly about them too. So here's the soldier beams and lagging. It's it's an I-beam that's driven completely into the ground, maybe 20 feet or 40 feet long. They call them H-piles instead of I-beams. I guess, if you get a chubby I and you flip it over on the side, it looks like a chubby H. But regardless, they put timbers in behind the flanges, and it's kind of a funny little mechanism. And in the process, you still need tiebacks if you're going down for this system. Because what happens is you'll dig down a ways like this, you'll put some tiebacks in place, and then you'll dig down some more and put some more tiebacks in place to connect it back with the wall. Here's some sheet piling. On the left, you're looking at more of a continuous bunch of sheet metal that's being vibrated and put in. But in many times, when the ground is a little more solid than that, even in Louisiana, we will drive sheet piles where they're more like what you see on the right-hand side of the page, where they've got a pile driver, and they'll drive the piles spaced apart a certain amount with a little bit less than the width of what these things are, so that you come back with again and drive some more piles in between those ones in order to make a continuous wall. And then there's shotcrete, which is a zero slump grout of sand and cement, sometimes with synthetic fibers mixed in. And when we say zero slump, it means we just put just enough water into the mix of this grout so that it will cling, that it will keep the shape that you put it in. And so it doesn't require any forming. And in this case, with shotcrete, they shoot it with an air gun. So they shoot it out of a gun of air, pneumatically pressurized and big compressor, and it clings to the wall, and they can keep building it up. And there's quite a bit of that that's done across the country in various ways. And it's a great fireproofing material also. But in this case, what you're really seeing is a mining operation. It's not something that we could do in Louisiana very easily. But it can be done, but it depends. Here's a hybrid system, but really what I keep this picture for here is to remind me to tell you that there's different ways of supporting that wall. You can't just put a wall up and expect it to stay there and retain earth or hold back some forces. You have to brace it, either with some diagonal braces like you see down at the bottom, or up at the very top before you get to the building brick or block, where there's some tiebacks that are going back at an angle. Soil mixing is where you can't use that in clay and silt like we have in Louisiana, but you certainly, if you had gravel and sand in your soil, you can auger through and mix Portland cement in and kind of mix it down into the augered shaft that you've drilled. And it's used a lot when there's contaminated soils, because you can basically build a wall like this all around your property that's got contaminated soil to keep the contaminated soil from getting caught in the underground flow of water. So you keep this from spreading and becoming more of a problem. So sometimes that's the first thing you do, and then you figure out how to clean it up afterwards. But you can end up creating a wall out of this stuff that eventually, when you're excavating the contaminated soil out, you do the same thing. You put tiebacks into the earth to hold this thing in place as you dig down to dig this deep hole to remove the soil and take it to a hazardous waste site where it can be cleaned up or burned off or something. Here's a mixture of the soil mixing where it's actually been made into a wall system. And then there's slurry walls. I mentioned that, but slurry walls are used in Louisiana. And the slurry system, what happens as you dig a hole, and like you see, and let me go to the next page because I've zoomed in a little closer on this diagram A. This first stage in A, we're looking at a trench that you're digging with a clamshell bucket where the clam, just like a clam, you close the bucket tight and nothing else can get in. So they can keep digging and digging, but in Louisiana particularly, you start digging a hole, and in many places, not just Louisiana, you can have the trench collapse on you while you're trying to dig it. And so what they do is they fill the trench with a quicksand-like material. It's called a slurry. Well, it's made of bentonite clay, a special kind of clay, and the mixture ends up not mixing and soaking into the walls of the trench that you're digging. So it works quite well to hold back the trench to keep it from collapsing while you dig. So these holes can get very deep. They can be 100 feet deep. But as you go, you're digging this hole, but it's full of this quicksand. You do have to have some proper guardrails to keep people from accidentally falling, or tie-offs to keep people from falling in here, because if you lost somebody in this quicksand, you'd never find them. And then case C in the center of the page, they drop a prefabbed cage of rebar in and into the slurry at the end when they've got the thing fully dug. Then case D, I'll get it, 1, 2, D, it's our fourth case, but case D, we're looking at a funnel with a long snorkel that is stuck down into the bottom, and they start pouring concrete in there. So they start filling up this cavity with concrete, and of course then they've got to pump off the slurry as they do that. So they can use the slurry for another job or another part of the job and such, but ultimately they fill this whole complete trench full of concrete. And this thing could be 2, 3, 4 feet thick, so a very thick concrete wall. Even at that concrete wall will fall over if you start digging. Like on the last case over here in case E, we're looking at where they've excavated this thing. And if you didn't have those tiebacks in there that you see in that drawing, that wall would eventually fall over. And if there's somebody in the way, they'd be killed. And so tiebacks are needed. So let me just show you a few other pictures. Here's the clamshell bucket on the left. Up at the top right, you see a cage of rebar being lowered into the slurry, and then down at the bottom right, you see a ready-mix truck pouring into the funnel that's going through the snorkel down at the very bottom, and they're filling this hole up. And then meanwhile, just to the right of the just to the left of the snorkel, you see a little pump that is pumping the slurry off as they're filling it up with concrete. So that's showing you up close that process. So something I should point out that maybe I should have put in a little earlier is that the bracing of these shoring can really be done in 3 basic ways, or a combination of them. You can do the cross-slot bracing up at the top, and that works pretty well with a trench because it's not too far across. A trench is defined as an excavation that is no wider than 15 feet. But the cross-slot bracing could be in the way if you're trying to put something in there. I mean, whatever you're building, it might be a problem having it in the way. So you could use diagonal bracing, or as they call it here, rakers. So rakers or diagonal bracing could be used, but maybe that would still be in your way. Or maybe if there's a very deep foundation, it might be not feasible to use diagonal bracing because the braces would be so long they'd be massive. So the last way, and I mentioned a little bit here already, but tiebacks, where you literally drill back at maybe a 30-degree angle into the soil and put a tieback into the earth that is connecting the earth to that wall. So in this diagram, you got maybe a sheet metal wall or something that you're doing that with, but it could be a much thicker wall. So the tiebacks, they'll drill through with a bit of a pipe sleeve, and then they insert a they put some there's a pre-stressing strand that they put in there, the same kind of strand we use for post tensioning, and then we put some grout in there under pressure, so they end up making a bulge, an anchor or so of concrete basically back in there that's bonding to that pre-stressing strand. With post-tensioning cable, if you know anything about that, they grease them up. We don't want grease on this. We need this to be nice, clean steel so that concrete can bond to it. Once that concrete is set up, then they can actually post-tension that cable so that it is actively holding the wall toward the earth and connecting it very well. Okay, so look at this picture. In this other picture, I had one strand, basically pre-stressing strand in there. An individual pre-stressing strand has 7 pieces to it, so maybe you'd have that. But in here, what you're seeing is that there are maybe 6 full 7-strand pre-stressing strands that are in each one of these receptacles. So they'll basically drill, and then they'll go and stretch those pre-stressing strands out to a high tension, put some little wedges in there so that when they let go of the strand, it's still under tension in the earth. And they've come down, this is about the 5th level down that they've been drilling in for this one. So you can have a very deep foundation here. This is used a lot with high-rise buildings so that they can have a parking garage down below the ground. And also, it could be the whole slurry wall system becomes part of the foundation of that high-rise. So when you dig a hole like this, you could expect water to collect. So what we normally have to do in many cases is dewater, but you even can do this in a place like Louisiana. We actually have a high-rise in downtown Baton Rouge that I know of for sure that has parking this below ground, even in Louisiana. And this is actually how you can have a basement in Louisiana, by having these pipes that are driven into the ground and hooked up to pumps that you suck the water out of the ground. And so if the water level was normally at that dotted line on the left-hand picture here, that dotted line would be the original water table, and then the dashed line below it that's swooping, that's the water table after you pump the water out. And so you can control and keep the water level and keep the basement dry. So this is what they have over at LSU in the quadrangle. All those buildings in the original quadrangle of the LSU campus have, in Baton Rouge, they have pumps that are lower than the basement, that they're always lowering the water table on an ongoing basis in order to not have damp, wet, moldy basements. So we call those individual straws or pipes that we put down, we call them well points. And then you hook them up to a pump, or you can connect them together like they did here. So this is a construction project. This would be a temporary system running around the site. They might have 2 of these, maybe one, so that you can access the property and stuff. But they've got a big manifold hooked up to all these well points, and then all that's connected to one big pump. So now let's pivot over to roadbeds and asphalt. So look at that nice brand new paved road here. You know, the lines on the road are really important to seeing at night. So one of the things about blacktop is you really can't see anything at night unless it's well defined with the paint. But the paint, it works very well. Okay, so there's some safety involved with dealing with asphalt, because the hot mixed asphalt is heated up to like 350 degrees. And so it's very dangerous in the sense that you can get very serious burns working with it. So we have to be careful and wear the right PPE, the protective equipment for this. The road mix asphalt is where we're actually mixing a solvent with the asphalt so that to make it more fluid. And then you're dealing with fumes that are flammable and toxic. So you might need to be wearing respiratory protection. Anyway, it's just a little bit about that aspect. Now, there's two things I want you to keep straight here, and that is that asphalt and tar are not the same thing. They're very different materials. So the two things that you need to know are two basic properties is that the asphalt is soluble in a petroleum, in a kind of a solvent of sorts, and so we can make a liquid asphalt. Because of that, where then as the solvent evaporates off, then the asphalt solidifies. So meanwhile, tar is so asphalt comes from petroleum distillation, from oil production, in oil and gas, and then the tar comes from coal production. It is not soluble in any kind of a solvent, and so tar is very different from asphalt and a very different source. Sometimes people, and I've done it myself growing up, called asphalt tar interchangeably because they're both pretty messy things to work with, but they are very different. Got a high hydrocarbon content in the asphalt, a high bitumen content, whereas tar has a very low bitumen content. And one last thing on this page, and that is viscosity. Asphalt is temperature viscous, way more temperature viscous than tar would be. That means that it reacts to temperature, and its ability to flow changes. So it's very solid at colder temperatures, and when you heat it up to 350 degrees, it's like syrup, runny syrup. And then they can mix it with the gravel and the sand to make that asphalt paving material that you see on the roads around us. So remember that basic definition. Really, the thing that's in brackets is probably what you need. It's simpler description. Viscosity is the resistance to flow. So yes, when the asphalt is cold, it's going to be very resistant to flowing. It's going to be hard. Whereas when you heat it up, then it's going to flow. So the viscosity changes with temperature. There was an original asphalt paving in this country was in Pennsylvania Avenue, right in front of Congress. They actually used some natural asphalt from the island of Trinidad back in 1870s. But there's no way from natural sources like that, or in Venezuela they have some. In the heart of Los Angeles, there's an original pit of of asphalt. They call it a tar pit, but again, it's really asphalt. Not enough in those kind of sources. We have to get them through the oil production. So what really happens here is you got an oil barrel full of oil, and we get the gasoline and the kerosene and the light gas oil and diesel and motor oils, and they'll take some of the other oils that they have too much of and break them down into, force them to become gasoline. But at some point, what's left in the bottom of the barrel is the asphalt. But it's still not worthless. It's very worthwhile. We can use it for paving roads, and we use it for roof shingles. We use it for lots of other products. So yeah, I've got a bunch of information about the basic refining process for oil. But ultimately, the thing is, down in red at the bottom, we've got asphalt. That's where our asphalt comes from. So what you need to know is the three basic types of asphalt binders. And really, there's asphalt cement, and then there's the liquid asphalt. And so case 2 and case 3 on this page are both liquid asphalts. So the asphalt cement is what we, number one, is what we use, that we heat up to 350 degrees, and we mix with the gravel and the sand that also has to be mixed up to about that temperature, and so it can be dried out and be the same temperature, so we can mix them all together, put them in a dump truck, rush them to where they're going to spread it out and compact it to be a pavement. The cutback is a type of liquid asphalt where we're dissolving the asphalt. Instead of heating it up, we dissolve it in a petroleum solvent. I think calcium carbide solution of some kind. And whereas the emulsion, the third case, is a type of liquid asphalt where we're dealing with water instead of a solvent. And in order to make oil and water mix, they don't tend to mix, but they do mix if you get soap involved. And so that's what we have, is an emulsifier, which is a fancy name for a very strong soap that helps us to mix the water with the asphalt in order to make it liquidy. And then we can mix it with gravel and sand, just like we do with the cutback or the asphalt cement, in order to make a pavement material of some sort. Okay, so remember that. We've got the asphalt cement that we heat up. We got the cutback that is used to make a road building mix. Or we have an emulsion that we use to make a road building mix. The road building mix, I think the road mix or the road building mix means that, well, way I remember it is, you can mix it on the side of the road if you wanted. There's no way you can do that with the asphalt cement for a hot mix asphalt mix. The HMA for hot mix asphalt that you see up in case number 1, that's where the typical paving, that's something like 98% of the paving out there is done in that fashion. Okay, so there is some tests that are done, and one of the tests that used to be done was to actually stick some asphalt in your mouth and try to chew on it and bite it to see how viscous it was. Hard on the dental work. So nowadays we have instead a standard penetration test for asphalt cement, where we have a needle kind of in a holder and we let go of it for 5 seconds and grab it again and see how deeply it went into the asphalt cement sample. This is not the same as the asphalt asphalt hot mix asphalt. We're not talking about gravel and sand being mixed into this sample. We're just trying to test the quality of that asphalt cement. It has to be done at a very specific temperature. Now I've got a sound effect that comes, so don't be jarred by that. Here it comes. Okay, well anyways, keep forgetting to get rid of that thing. But anyway, I got a sound effect. And what this is doing is showing that, after 5 seconds, which seemed like a long time. It doesn't seem like a long time, but it is fairly long when you're talking about it sinking through a soft material. And we're measuring how deep it went. Anyways, so that's one kind of a test we call the asphalt penetration test. You do not need to remember the names. I just want you to understand these concepts, because when you're bidding a job, you have to be familiar with the fact that there are some tests and know some telltale signs for this, because if there are tests, they have to be done by qualified people, which means you're going to be hiring and paying for in your contract a testing company to come in and do these tests, or take it to their lab for them to do a test or something. So back to viscosity, the stuff on this page. Right now I got a picture of peanut butter on wax paper along with some ketchup, and you can see they're at a sloping, and it's running down the page. Well, the peanut butter is staying put, so it's very viscous, whereas the ketchup is running. It's not as viscous. So it just gives you the idea. When we talk about high viscosity, we're talking about something that's got a strong resistance to flowing anywhere. We also do that with motor oil. Down at the very bottom, you see 30 weight or 10W30 motor oil is less viscous, more runny, less viscous than 20W50 weight motor oil. So, I've got a whole thing on that on this page, but in the interest of time, I'll skip past this. But for motor oil, they all these measurements are made at 210 degrees Fahrenheit. So you had to have a very specific temperature reading. Apparently we can start looking through the viscosity of peanut butter compared to ketchup, compared to maple syrup, olive oil, cream, water. Water is considered non-viscous. All right. So resistance to flow. So a high viscosity means it's very thick. So when the asphalt is cooled, it's more viscous. When it's heated, it is less viscous. So that's just to make sure you really have the terminology in your head about what viscosity is. So there is a standard for dealing with viscosity and dealing with the road building materials for paving called SuperPave. And it could be mentioned in your specifications for the drawings for the project that you're bidding, that you're estimating. And so this is the kind of reason that you need to know this a little bit, just so that you know that, I better get a subcontractor to go bid this part out. So SuperPave, created in 1995, or officially created in 1995, it deals with the selection of materials, what possible materials you have in the area to use. It deals with the design aggregate structure, so you're going to figure out of that how much of a well-graded gravel you're going to have with a well-graded sand material, and the selection of the amount and type of asphalt binder that you're going to use. And some other things about the actual design criteria for the region. In general, you have a certain air void content, which is usually 3 to 5% air content once it's compacted in place. They can look at the mineral voids and the voids between filled with asphalt and the dust proportion. There's all kinds of things that they can get into the weeds on. I just want you to understand it's a design specification system that is used throughout the industry for just about all kinds of asphalt paving. So anything about SuperPave that's listed in your specifications, you need to pay attention, because that means if you miss and ignore that, you're going to lose money on that job. Okay, so HMA sounds like a Health Maintenance Association or something, eh? No, it stands for Hot Mix Asphalt that we've been talking about. 93 to 97% size and proportion aggregate that is heated to approximately 325 degrees and then bound with the asphalt binder with a temperature of around 350 degrees to get this mixture, an asphalt-based concrete, basically, that you got to hurry and get to a place where it can be compacted in place before it cools to about 260 to 275 degrees. So just remember that we're heating this stuff up to somewhere in the mid 300s. You get to about 400 degrees and you start causing damage to the asphalt. So no higher than maybe 375. So the air voids is what I want to focus at. Hot mix asphalt is typically designed with 3 to 5% air voids is what they specify. And that is not while it's mixed, it's when in the back of the dump truck and stuff, but when you finish compacting it. So whoever's compacted has to figure that out. So it helps to provide structure sufficient to handle the loads, especially dealing with temperatures. And so there is something magical about having 3 to 5% air voids where it helps to keep you from having troubles with your asphalt. So pros and cons of asphalt compared to maybe concrete for paving. Well, it's versatile, it's fast. Heck, you can pave it and people can drive on it right away. It's flexible. You can contour it, and you don't need concrete forms, so it has its advantages that way. When the cost of oil is low, when oil prices are low, it's very competitive. It's hard to compete with asphalt. When it's high, then all of a sudden concrete starts looking better and better. So the economics can change depending on the economic environment that you're dealing with on this. Big plus, doesn't really matter here in the south, but the asphalt is not affected by ice control. So when we put salt on the highways in the wintertime, that's very hard on the concrete, but it's particularly hard on bridge decks where the salt can soak through the concrete and get to the reinforcing that's in the bridge deck. And so they have to be very careful on bridge decks, and they try to seal that concrete as well as they can. But ultimately, if it's paved, you didn't have to worry about that issue so much. But there's other troubles with using asphalt on a bridge deck, but still, ice control is not an issue for asphalt, and so that's a big deal. It's quieter when it's smooth. I would just say that in climates where we have a lot of snow, they purposely have to give a textured surface to the asphalt, which makes it noisy, so that you can have good traction in the rougher weather. It's easier on the eyes at night. There's less glare, so that's a helpful thing. But again, and then the big negative is that asphalt doesn't do well in hot climates. So we have trouble here in the south with asphalt, but it's even more troublesome in very hot desert communities in Nevada, New Mexico, Utah, Southern California. The hot temperatures really are brutal on pavement. Okay, so the super paved design does have something else I want to mention. That's the second bullet on this page. The mix specified by the anticipated traffic volume, which we measure in ESALs, equivalent single axle loads. So an ESAL, ESAL, is an equivalent single axle load, and that load is defined as 18,000 pounds, one single axle. So an 18-wheeler fully loaded, each one of those axles with 4 wheels on each one of them, is allowed to have a maximum of 18,000 pounds on it. So in the trailer of an 18-wheeler, you have 2 axles back there. That's 36,000 pounds. And then the tractor, the truck itself, the back 2 axles that are on the back of the truck, that's another 36,000. So that's 72,000 pounds. And then the steering wheels, the 2 wheels on the front of the tractor, are allowed to have 8,000 pounds. So out of that, that's 80,000 pounds. But it all comes back to this idea that on a single axle, you should have no more, with those 4 tires, no more than 18,000 pounds. And so that's considered a single load. One axle rolling over fully loaded like that does 1 unit, 1 ESAL of damage to the road. It's all about the flexing of the pavement, the squishing and the flexing of the pavement every time one of those axles goes down the road. And an 18-wheeler has 4 of them, plus the front wheels, which are not so much of a problem, but those 4 wheels they're doing a lot of flexing of the pavement. The pavement wears out. We design pavement to last. Normally, the design criteria is often 20 years. But if you get a lot more truck traffic on a road than you designed for, then that pavement can run off much faster. So when you look at a standard 18-wheeler, the Highways Department considers that a 3S2, where you have 3 axles on the the tractor itself, and then the trailer, you've got 2 more axles. So that 18-wheeler inflicts 4.2 ESALs of damage to the road when it's fully loaded. When you look at this table here, there's the 18-wheeler down at the bottom, 4.2 ESALs, and the dump truck is somewhere around 2, might be 2.1, 2.2, I think, could be, if it's fully loaded. That's about 40,000 pounds. And it gives me an excuse to show my first real car, and that was the 64 Dodge Polaris 500. Anyways, it's about 4,000 pounds. And so you see how it's only good, only does 0.0006 ESALs of damage driving down the road compared to the 18-wheeler. So just think about this. The 18-wheeler does 7,000 times more damage going down the road than my 64 Dodge. But the thing is, 7 times more damage, but it's only 20 times heavier than the truck. Well, 20 times is a lot, but 7,000 is a lot more. So when we're looking at damage that trucks do, they do far more damage than all the other vehicles on the road combined. It's not even close. I'm saying that on average, a single truck is doing the damage to a road of 7,000 other vehicles going down the road on average. Because by today's terms, a 4,000 pound vehicle is a fairly heavy vehicle. That's getting close to pickup truck weight, whereas lots of cars are 2,000 or 3,000 pounds that are out there. So, okay, so that's enough fun. with that. There's some other tests that are done besides the penetration test. There's a gyratory compactor. They take samples from the street. They drill a hole with a hole saw out of the street, and they take that big hockey puck of pavement back to the lab, and they compress it in this gyratory compactor, which simulates the effect of traffic over the life cycle of the asphalt surface. They can kind of simulate how many esals of damage this pavement can deal with, and that tells you how many years it's going to last. There's an old system that was around before that called the Marshall test, and that was sometimes still used today, but it's a similar concept, just not quite so fancy. But anyways, the SuperPave design system has specifications for doing these tests, and those can show up on your specifications, and you got to pay for having some of these tests done. So that's why you need to know about this. Okay, so remember, AASHTO stands for the American Association of State Highway Transportation Officials. So AASHTO is a big long abbreviation, my goodness. But anyways, all the state and federal transportation officials belong to this organization, and they set these various standards for how these tests operate and other evaluations too, and some of the things about the SuperPave specifications. Here's some other samples, and this helps to remind me to mention that there's different thicknesses of pavement. You can have a 1-inch thick pavement. Might be what you do on a driveway in a yard, for a house. 1.5 inches is really a common standard thickness for pavement, but most roads, even in neighborhoods, are paved maybe 3 inches thick. But it was usually done in 2 passes. They would pave down in 1.5 inch pavement and then another. And so when they go to repave a neighborhood, they might grind off one surface and still leave 1.5 inches behind. Grind off 1.5 inches and leave another 1.5 inches behind, so they can come back and repave. But pavements on busier roads could be multiple layers, or they could be thicker layers. So you see 3-inch thick pavements on many major highways, and interstate quality pavements would probably be 10 inches thick. So you can start seeing it gets to be a lot of money when you start having to do that because of the truck traffic. So a lot of times it's way more practical on the interstates to use concrete. Or what happens a lot around here is you might start off with a concrete paved road. When it wears out and needs to be replaced, they may patch it up and then pave over top of that with with asphalt, because the asphalt on a concrete surface is kind of a magical combination. It works out very well for a durable surface that lasts longer. If it's put down right. That's always the big if. Here's another test for various things. Anyways, so looking at some sample pavement here. If you have one with too many air voids, that it's because it wasn't compacted properly most of the time. And so if it's got too many air voids, then the water can flow through it and get through and separate the layers of the asphalt, or it can wash the soil out from underneath the pavement. So that's a problem. So not compacting it well enough. And that's usually not because they didn't want to. It's if they run out of time and the stuff is cooled off before they get a chance to get it compacted. That's how that usually happens. So the stability of the mat and also the permeability of the mat, of water to flow through it, are problems. Here, I showed you this picture when I was first mentioned SuperPave, but I forgot to mention what the problem was here. It's over-compacted. And so if you compact it too much, if you get beyond to less than 3 to 5% air voids that we need, then you can get this gooey, kind of like a used chewing gum that has no structure, and so it can't take a lot of loads without doing something weird. That's what happens. And so, but still, the rutting won't happen from the cars. The rutting won't happen there. The rutting happens from the big trucks. So these are truck tires that are making these ruts. Here's a couple of things that are kind of similar. The alligator cracking and the block cracking, typically from structural failure of the subgrade, the base underneath, the road building, whatever is underneath this pavement is not strong enough, and so it's kind of collapsing because of that. Whereas here, we've got two that are kind of related to each other, longitudinal cracking and transverse cracking. down at the bottom, the transverse cracking, it's cracking across the road as a line. And that can happen when you don't have control joints. You've got to have, as soon as we pave, we also have to then do some saw cutting to put some saw cut cracks to cracks in there, and then we fill those cracks with a caulking of either asphalt or tar in those cracks. A caulking of sorts to keep the water from getting up underneath again and washing out or separating layers. Up the top, you got longitudinal cracks. We're looking at the cracks that are running from the front, from us out into off in the distance here, between the two lanes, because they typically pave the lanes separately, and then you can end up with this natural tendency for the two lanes to move about expansion and contraction side to side in a way where they back and forth along against each other, causing this irregular crack. So they run a straight line saw cut along that seam, so that as those two move back and forth, they won't create broken up pieces that become potholes. The transverse cracking can be just like what you see in this bottom picture, and so most transverse cracking is actually joint reflective cracks cracking. So if you don't put a saw cut in the right place, you can end up with, if you've got concrete underneath, for instance, then the concrete has control joints, and you need to make sure that your saw cuts are in line with that. So that's one important thing. When we do pave over concrete, we have to mark out where those control joints are in the concrete, because we need to make our saw cut crack lines. Those cuts have to be in the same place right above it, so that and then we fill them with a joint compound of asphalt or tar that seals that crack, but you allow it to move back and forth without tearing apart the road, is what the idea. The idea is to have a longer lasting road and not have these things eventually cause the road to fail. Slippage cracks, up at the top you see a kind of crescent shaped cracks or tears of the pavement, typically it doesn't end up bonding as well as it should maybe, but sometimes between the layers we'll put down a tack coat of a liquid asphalt, and then you're the one that accidentally drives through it and gets it all over your car, but it's meant to join the two layers. So maybe if that's not done properly, that can be a problem, but mostly it's because of heavy truck traffic and such, that when they hit the brakes at an intersection, that ends up sliding the pavement forward on them. Okay, that's enough of that. Let's go and look at a little bit about the batch plants themselves. So here we got a batch plant where the guy thinks so highly of his batch plant, he thinks that it's at the end of the rainbow. It's the pot of gold at the end of the rainbow here. Okay, we're looking at a batch plant. They all look something like this with these towers and tanks. They've got tanks of asphalt, and they got to heat up the asphalt, and so they have a boiler for that. And they have to heat up the sand and gravel so they can dry it out. You can't have any water or moisture in the gravel and the sand. And they all have to be heated ingredients so they can be combined and mixed, and then they'll run it in a conveyor belt system all the way up to the top of one of those towers and dump it in one of those towers that has a hopper at the bottom. And then you drive the trucks underneath the hopper, and they dump the asphalt in there, and the truck takes off and goes to wherever they got to pave. Asphalt is sold and bid by the ton. So you have to know, okay, a ton is 2,000 pounds. And so however number of tons they put in that truck, they weigh it. So that when they go and they weigh the truck before, and then they weigh the truck afterwards, so they can figure out how many tons they put in there. And that's how they know how much to bill for. So anyways, let's see here. Then the truck comes out and drops the asphalt into a hopper of a paving machine so that they can spread it out and kind of do a little bit of compacting with the machine. And then you have a compactor like you see in the foreground here that is compacting it for the final compaction, or much of it anyways. So that compaction is the feel and the skills of this operator of the final compactor. It's so important, because it's only out of that they kind of get it compacted just right. because the testing that's done for what the air void content is, the 3 to 5% air void content we need, they can really only do that in the lab after the fact, and that's too late to do anything about it. So this guy has to kind of do a very skilled job here, because if he gets that wrong, the whole thing has to be ripped up and started again. So here's another smaller operation. Got a little hopper they're dumping into, and maybe something a little simpler here too, and then they're compacting. Here's one that's contoured for curving, maybe for going around a corner and a clover leaf or something of an interstate. And then, I mentioned the liquid asphalt. They put down tack coats between layers, but they can also spray the liquid asphalt down as a coating on top of a parking lot to make it look like it's new, even though it's not. But it makes it all look fresh and new. But it also helps if you have to repaint some faded lines in the parking lot. You can best do that just by erasing them, by coating it with a fresh coat of asphalt. Then you can go and put new lines down. Okay, so when you're looking at the pavement, okay, what happened here? I lost my picture somehow. I lost a picture. Oh no, I'm thinking of the wrong page. Okay, so anyways, 3 to 5% oil voids. I keep mentioning that because I want you to remember that for a possible test question. Let's see, proper mixture. Some places I've had some different temp numbers, but in general, it's something to remember that we heat up the asphalt to 350, heat up the gravel to somewhere in there, maybe the 325 area. We mix them together. We try to get the stuff to the batch in place before it cools off to somewhere around 260 or 275, and somewhere in that range it becomes useless to keep trying to compact it. And if you don't have it right by then, you're in trouble. So they have a really tight window. This is the page I thought I was looking at. So looking at this page, there's many different layers in a road. And so when we're looking at the road bed, you start off with some quality aggregates down the bottom in the subgrade, and then you put some better quality aggregates in the subbase. And then maybe the base course could be concrete, or it could be a high-grade, expensive limestone road building mix of gravel and sand, well crushed gravel and angular sand, well graded all the way down with lime powder mixed into it, and then compacted. And then you got the actual surfacing, where you'll have a binder course and a surface course. So most paved roads, even in neighborhoods, you start off with 1.5 inches or your binder course, whatever that thickness is going to be, of asphalt, and compact that, and then you put another surface on top of that, which becomes the final surface. And so when they need to go in, so when you're looking at this list, trying to remember, there's a subgrade first. I've put them in opposite order here. So 1, 2, 3, 4, in the same order that it is on the diagram. So the subgrade ultimately carries all the traffic load, so it must be prepared and structurally sound. The subbase is a better quality aggregate, often layered on top of the subgrade. And then the base layer or base course is placed on top, which could be a well-graded limestone road building mix, or sometimes it's an asphalt aggregate mix, a low-grade version, or it could even be a Portland cement concrete of some sort, sometimes a lesser grade, or it could be a high-grade one because you maybe already had a concrete slab on there because you're just putting new pavement on top of that. And so finally, the asphalt layering surface is the very finished layer, which is the one that has to be all nice and pretty. So then they got to paint the lines. Well, you can see here that the paint truck stops from no one, or no being here. Eh? But anyways, now we're coming back to the last little area dealing with foundation science again. So in this picture, we've got a shear wall, which you remember we talked about. Shear walls are the vertical structures that make something rigid, and then the horizontal diaphragm is the part that's horizontal in a floor system that makes a structure rigid. You need both in order to make your building hold together and withstand the various forces. Here they're building shear walls out of concrete with lots of rebar in them, and collectively they will work as part of a system here. So that's still basically, in that sense, part of the foundation. Here we've got a house foundation where because of how the ground on this front side of the house is is not going to be backfilling the basement, maybe, or not protecting the foundation properly, you have to step it down. And so every time that you're going to have in a place where the ground can freeze, let's say you've got to protect it for 4 feet of frozen ground, then you got to build below 4 feet. Then as you come to an area at the front of the house here where you're not going to be backfilling and protecting that from freezing, then you have to step the foundation down way below where you think you need it. And so that's just what we mean when we talk about stepping a foundation down. And even though all of this slab could be all at the same height up at the top, all the way across, if you're going to have it unprotected, you've got to think that through. So you can't just go dig up a foundation and decide you're going to change the contours of the ground, because the foundation, you'll end up with the frost heaves out of that deal. Ultimately, I had some pad footings here for the columns in here. Well, every column, if you're going to have a standalone column, it has to have a pad, like a snowshoe, to spread the weight over the soil, over a bigger area. Otherwise, that column will just sink into the soil over time. Whereas the continuous walls of a basement running around, they run on a wall footing or a continuous footing. Sometimes we call it a strip footing. So it could be 16 inches wide or it could be 24 inches wide, and then the basement wall tends to sit right on the top of that in the center. And we talked about slab on grade construction, which is extremely common here in the South. Crawl spaces or pier foundation is kind of a variation on that, and that's fairly common. But what's not very common here is a basement, because of the water table, of course. So when you have a floating foundation, it can sink over time, which can be a problem, So if the soil can't support the weight of your building, the engineer would figure that out, then they have to go and use some other means of a deep foundation. And generally deep foundations, you use piles or piers of some sort. So that's what I've got on this page. So we're coming back to talk about them a little bit. So in Louisiana, we mostly use what you see on the very right-hand side, the friction pile. Whereas if you get to a place where the bedrock is closer to the ground, they can have what we call end-bearing piles, where you drive them down till they hit bedrock. And you can have caissons that are drilled piers, basically, where you auger out the hole and then you pour concrete, a cage of rebar and concrete in the hole to make a pier in that fashion. And so if they're going right to bedrock, that works pretty good. But I know that we've done some caissons like the very left-hand one here in Louisiana, but here we have to use the slurry mixture like we were talking about for the slurry walls to fill up these things as we auger so they don't collapse. Then we drop the cage of rebar in, and then we pour concrete and pump the slurry out in the same way for caissons or drilled piers. So the thing that I want you to have the asterisks on the red asterisks down the page down here for is that friction pile over on the very right-hand side. It says if the bedrock is very deep, meaning you can't reach it, then when I ask you what kind of foundation are you likely to use for a heavy building, it's going to be friction piles is what you need, because you just can't. If the bedrock is 300 feet or more below, you're definitely not going to try to reach it. It's just not practical. And for most cases, it's not practical if it's more than 20 feet or 40 feet below. So these drilled pier caissons, that's what I'm showing you pictures of here. They've already drilled the pier hole, and they're dropping a prefab cage of rebar in, lowering that in with a crane, I guess. We'll get back to that in a minute here. Here's some precast piers. It could be, precast concrete piles that could be driven into the ground. So I should have put them in a different place, I suppose. And when you do have piles or piers, we connect them together with pile caps and or grade beams, depending on how the construction goes. So in this case, in this picture, the pile caps are also connected and poured integrally with the grade beam. So when we say grade beam, when we're talking about the grade, we're talking about the ground. You can replace the word ground and grade interchangeably, and they mean the same thing in construction. So a grade beam is beam on the ground. That's all it means, really, as opposed to a suspended beam up in the air. Okay, so looking at the piers, you can see them now. They've been poured. There's rebar sticking out of them. There's about 3 of them I can see, 4 of them I can see in this, almost 5. And they're preparing the ground in between because they're going to pour concrete beam in between them and interconnect them all together. The gravel is often used to prepare a better base for your permanent grade beam to be, or your slab and grade. Nothing better. It instantly compacts. Underpinning, the process of placing new foundations between existing structures or to strengthen or stabilize them. So you've heard of foundation repair companies that come in and they'll go and dig some holes around your house and then jack up the house and pour some new foundation up underneath that to help keep it in place. When you're supporting a building temporarily here, while you're doing all this, we build things like you see those heavy timbers that are kind of built in nice little pattern here to kind of like a log cabin almost. That is called cribbing or cribs. So another kind of bit of a terminology. So underpinning, the process of placing new foundations under existing buildings generally. And cribbing is where you're temporarily supporting while the foundation is being built. Okay, so here on the left you see the pile driver that was over at the library, the main library at Independence Park. I've got a lot of pictures from that. And up at the very top picture you've got some 6 piles that were driven into the ground, and that's what they look like when they got a finish beaten on them. And then they'll go and cut them off at exactly the height they want, get it all clean, and just to be on the safe side, they'll use some copper sulfate on the top because to make sure that no bugs can get in. These are treated, they're pressure treated logs, but you still typically want, when you cut it particularly, to go and re-protect it because the pressure treated doesn't get as deep into the center of the core of the log. And then they'll put a whole bunch of reinforcing here in this thing, connecting the logs to a mat of steel, and pour concrete all the way up to where those paper cups are stuck in the dirt. And when I go to the next page, well, to this page here, you can see the paper cups. They filled the concrete to that height. Still have some rebar sticking out. That'll be in the grade beam. And so over on the left-hand picture, you can see how they are keeping that steel and the grade beam together. So they all get poured together as a group. And here they are continuing that grade beam all around. And that grade beam at the library ended up going all around the whole building. And it's basically below ground because here it is, not the height of that concrete slab that you see there, but that next step down, that's the top of that grade beam. To never be seen again once they get it all finished with this. Retaining walls. That would be a horrible place to take a nap because that thing can come down any day, any time. You just never know. It's ready. It's ready. So that is the thing that seems to flummox many a person where they don't understand when they go build retaining walls that you can't just stand up a chunk of concrete and hope it to stay there. The soil on the other side will compact and push against it, and then it'll move it over a little bit if it can, and then it'll settle some more and compact some more, so it just like a bunch of wedges keep working, eventually brings that wall down. And sometimes that means it kills people. So concrete retaining walls have to be made much more substantial than that. And so what you're seeing in this cross-section of this drawing is it's a slice through the wall. So the length of the wall is coming out toward us and away from us here in this picture. So the rebar is showing in there and everything, but all this concrete, notice that there's really as much concrete below the ground as there is between the stuff. That's not by accident. That is normal. So that for this thing to tip over, you've got to lift up that footing, which would be, require a lot of effort to lift all that earth up above that footing, And so there's also other kinds of systems for retaining earth, but they all rely on tying back to the earth in some fashion. So in this way, the wall is like a big chunk of angle iron in a sense that can't be tipped up because you'd have to lift all that dirt up for it to happen. Whereas this picture is showing other systems that would reach back and use tiebacks or tie-ups to connect the earth so that it won't tip over. Oh yeah, the one last little area here is about drainage. So behind a retaining wall and behind a basement wall, you can't just pile the dirt and declare victory. You can't just pile a bunch of dirt behind that wall. It's got to be compacted, first of all, along the way as you go up, but you can't just put sand or silt or clay against the wall, or you have a free draining gravel that you put down. And so I think I got a picture right here that's showing the gravel. And so there's a waterproof membrane here that they've sprayed on there to keep wet moisture from getting in there. They've also got another membrane he's putting up there that's basically being held up there with those sticks while they backfill with gravel, and they can go back, keep going back and forth as they build with dirt and gravel all the way up. But just they also have to have a place for that water to go. So that typically means you've got a drain tile down at the bottom of all that gravel, at the bottom of that wall, so you can send that water somewhere else. So this is all about trying to keep that basement wall and that basement dry. So there are techniques that are used nowadays for that exact purpose. And if you don't get that right, it doesn't go well at all for you, because you got mold problems, you get water problems, flooding is never a good thing. Okay, that other thing is in this picture here. One last thing I thought of I should mention is that silver duct tape that's in the closest to the bottom of the picture is the beginnings when they finished plumbing it up properly to the top surface, where they give a clean out so that a plumber can come along with a plumber snake and literally ream out that pipe to keep to unclog it if it got clogged over time. But we often will use geofabric in places, in ways, in order to keep the dirt from finding its way back in there. So with that, we got a few useful links at the end here for several pages, about 3 or 4 pages here of them. These are idea places you could go to for ideas about what to write your essay about. You've got a 1,200-word essay that's going to be due toward the end of this semester, and it's good to start thinking about it now. In fact, I have an outline assignment coming up in a few weeks where you will need to submit an outline for what you're going to write about so that you get a chance to think it through a little bit. But all of these are handy links that would be useful to look at for that purpose at least. Okay, well with that, this house looks like it's seen better days. Foundation problems galore, huh? Okay, so, well, that's all we have for this chapter 2 now. And our next chapter will be chapter 3, dealing with wood as a material.